their first offspring. If you keep following this pattern, what keeps happening is they're going to keep going, but you wind up with one pair of rabbits, then another, then they're still there. Then you have two pairs of rabbits. Then you have three.
Five.
What do you think will happen next?
8.
8.
13,
etc., etc., etc. So it's fairly easy to say for the Fibonacci rule that a sub n is a sub n minus 1 plus a sub n minus 2. You add the first prior terms, and a sub 1 is usually given as 1. That gets a little tricky on the first term. Well, usually what they say is they say a sub 1 equals 1, and they say a sub 2 also equals 1. And that lets you jump in at a sub 3. So those are all the prior conditions need to be given to make Fibonacci's rule make sense as recursive.
Like, let's say we were given a sub 1 equals 1, a sub 2 equals 1. Then can you just put it into the equation so I can see that?
Well, then you would say a sub 3 equals a sub 2, n minus 1, plus a sub 1. And you were given the 1 and the 1, so now a sub 3 is 2. Because you were given those two pieces of information. After that, you would say a sub 4 equals a sub 3 plus a sub 2. Well, a sub 3, you just found out was 2. And a sub 2 you were given was 1. So a sub 4 is 3. A sub 5 then is a sub 4 plus a sub 3, which in this case is 3 plus 2, which is 5. And whether you follow this recursive rule or go through your rabbit procreation chart, you'll get the exact same numbers at every stage. This is one of the easier, more interesting recursive rules. Good luck if you try on your own trying to turn this into a general rule. That's not easy. That's not easy at all. Incidentally, a lot of... I've seen it, yeah, but I forget the preconditions seem really weird to me. I'd have to look it up again. I don't remember what it is. This is an interesting numerical sequence. It turns out this doesn't really describe any mammals breeding anywhere on Earth, but there are plants that follow patterns like this. They give off sprouts and buds in a fairly predictable pattern, like a bud appears, and then the bud is able to produce a new bud, and then a month later, the new bud is able to produce a bud, etc., and the old bud is still producing buds. So this actually describes the pattern of the spiral in sunflower seed plants, sunflower seed plants, that's redundant, sunflowers. And this, also there's certain plants that have branches. I'm not sure, I don't know that one. But there are plants where if you look at the branches, each branch continues to grow, and at regular stages, each branch gives off a single other branch, branches off, and those branches branch off again, and the Fibonacci sequence will accurately describe the number of branching pairs over time or distance down the branch. So this does show up in nature semi-regularly, but it's not a particularly useful predictive rule of anything. There are two types of rules I'm going to give you homework on tonight, two types of sequences. The first is called arithmetic. And this is, there are so many different types of these sequences. This is where we're starting to break it down to just a few simple ones to get you used to it. Plus these do show up tiny bit in calculus, usually just to prove other things. Arithmetic sequence means the numbers have a common difference. We just did two examples of them. 1, 2, 3, 4, 5. The common difference is 1. 2, 4, 6, 8, 10. The common difference is 2. See if your book has a more interesting example of them. Now, sometimes they're a little harder to see. This one shouldn't be too hard. I don't need to look at this anymore. goes down by which?
1/2.
Yep. And if it goes on forever, we'll keep doing this. So here the common difference for this example, we would call the common difference a D, and we would say it's negative 1/2, just to keep the notation. There's a pattern to arithmetic. I don't do that example, I'll do this a slightly faster way. There's a pattern to arithmetic sequences in series, which is if you're going down by the same amount every time, it starts to behave like slope on a line. There's a little bit of a y equals mx plus b quality to this. So for an arithmetic sequence, we can always say that a sub n equals a sub 1 plus n minus 1 times d. Your nth term will always be your first term plus 1 minus whatever term you're looking for times your common difference. The common difference is similar to slope. This is not actually common, this does not correspond well to a y-intercept, unfortunately. This corresponds to like what y would be when x is 1, not 0. So that throws that off a little bit. But D does work well for slope. So for this sequence, I can tell you right now that a sub 12, without going 1, 2, 3, 4, 5, 6, 7, 8, 4 more places, is just going to be 3 plus 11 times negative 1/2, which is 3 minus 5 and a half, or negative 2.5. If I've done my arithmetic correctly, then I know the 12th term of this arithmetic sequence without having to continue subtracting halves for the rest of my life. All arithmetic sequences follow this general rule. All of them. If you can make sure you see it's an arithmetic sequence. That can be kind of hard with fractions and decimals sometimes.
How's it 3?
Pardon?
How's it 3?
What was the a sub 1 is where I start with this rule, right? What number is in my first place?
Let's say some 12.
I was looking for a sub 12, and my formula says to start at a sub 1.
Oh, so that's a sub 1.
Yep, and then a sub 1 is whatever's in the first spot.
Alright.
Remember, a sub 1 just means, this subscript 1 just means which place we're talking about. That's what that subscript means. Good question. Arithmetic are pretty straightforward. How hard would it be for you to tell me the sum of the first 4 terms in that sequence?
It wouldn't be that hard, just like that.
Okay. So what is the sum of the first 4 terms in that sequence?
It's 10.
Is it really? I think you're right, but
Wait, 3 plus 2 is
5.5. 6, 7.
No.
I'm getting 9.
Oh, okay, because I just did 3 plus 2 is 5, and then 2 plus 1 is 3 plus 1. The halves together is a 9, 4. So yeah.
That's 9?
Yeah, because
You're okay.
3 plus 2 is 5, 2 plus 1 is 3, and 1/2 plus 1/2 is 1.
5 plus 3 plus 1 is 9. Nicely done. I like how you grouped that. Okay, so it's 9, right? How much fun would it be to find the sum of the first 20 terms?
Oh, Lord.
For sure.
How about the first 100 terms?
Probably not worth it.
Probably
Oh.
not worth it. You guys remember my example of little Carl Friedrich Gauss and his truly genius way for adding up numbers? He was asked to add up all the numbers from 1
Oh, yeah.
to 100.
So what he did was like,
He did that.
Realize that
1 plus 100, 2 plus 99, and so on.
Pairs, right. Tyler, what did you say there?
So 1 plus 100, 2 plus 99, and so on down the list.
And what do those all add up to?
101.
Okay. And then how many pairs of these did he have?
50.
50.
Multiplied by 50.
Yep, so that was just 50 times 101. You will be shocked to hear that little Carl Friedrich Gauss, who supposedly by legend came up with this at 10 years old in his little schoolhouse in Germany, you'll be shocked to hear that he went on to do a lot of work in number theory. And he went on to invent a lot of what I'm teaching you today, including this formula, which is if you know you're looking at an arithmetic sequence, numbers that go up by the same amount each time, then the sum of the first n terms, however many terms there are, is n over 2 in 100 numbers. You wound up multiplying by 50. Times what you get when you add the first term plus what you get when you add the last term.
Wait, so would that be like the bottom? That would be for this one, it'd be 3 minus 1/2, right? Either 2
If I were looking for the sum of the first 1, 2, 3, 4, 5, 6, 7, 8 terms, yes. If I were looking for anything past that, I'd have to
So in
figure that
order
out.
to do S20, we'd have to do this other
Right.
formula first, and then.
Yep, it's no longer tedious though, at least it's not the same. So, what is a sub 20 based on my general rule over there?
So a sub 20 would equal 3 plus 19 times -1.
Okay, annoying, but better than adding up the first 20 terms, right?
Right.
Okay, or going out, or doing the common difference 20 times. 19 times -1/2 is going to be
Minus 9.5.
minus 9.5.
Wait, I'm confused. 20 over 2 isn't 3.
A sub, good call, Jen. Okay, this general rule over here,
Why did you jump to that equation?
we have to find the 20th term first. In order, we have to, what Michelle was noticing, and I should have checked, is that there's an a sub n in my formula.
Right.
And I don't know what the 20th term is, so I have to do this first. The general rule for a sequence says that the nth term, like whatever's in the 20th place, if it's an arithmetic sequence, only if there's a common thing being added or subtracted, whatever's in the 20th place is going to be whatever's in the first place, that's where we got the 3 from, plus the number we're looking for, 19, times the common difference, we're going down by 1/2 every time. So that's where that 3 came from, it's the a sub 1. So this is -6.5. I wrote that too close to that. So now that I know a sub 20, I can fill this in. I'm looking for the 20th term, so it's 20 over 2. A sub 1 is 3, plus -6.5, my 20th term.
That equals 10 times
So it'd be
-3.
So that's gonna, which is 3.5, so that's -35. Am I right? Daryl and I agree we're usually right.
Yeah.
Daryl's better at that than I am. So, not my best use of the board space. So which would you rather have done? This formula to find the 20th term and this formula to find the sum of the first 20 terms, or actually gone step by step and counted them through?
Step by step.
I would enjoy this.
No, up to like, I say 4 terms, I do the adding step by step.
Depending on the,
But I'll use this formula from then on.
that's probably pretty smart, depending on how ugly the sequence is. But do you see how this is exactly what little Carl did from 1 to 100? And he just realized this method will work for any numbers in a row, as long as
There's a certain pattern to it.
there's a very specific pattern to it. It's an arithmetic pattern. As long as you were adding or subtracting the exact same amount in between those numbers. Yes, sir.
Is there a similar method for like if you're multiplying?
Did you look at the book? Did you look at the book? Follow me over here. I was only going to talk about 2 different types of sequences today. The next one is called, I am answering your question, Joey, believe it or not, geometric.
Have you done this? Not like this, but like last year.
Possibly. It is in a lot of Algebra 2 books, but not every class gets to it. This marker is the weakest link. It is too weak to live. Can't believe I missed that. Okay, geometric sequence. is one where the recursive rule for a geometric sequence is a sub n equals something which I'll call r multiplied by a sub n minus 1. So the recursive rule, if you're going to describe the nth term in terms of whatever happened right before it, you multiply. So an example of a recursive rule, 2, 4, 8, 16, 32, 64, dot, dot, dot. A sub 1 is 2. My common ratio is also 2. So I'm starting at 2 and I'm doubling it every time.
What would you write if it was plus 2? Would it still be 2?
Then it would be, you missed the way we just started that. If it was up 2, 4, 6, 8, 10, then that would be an arithmetic sequence, which we just did.
Geometric is when there's
Multiplying, yep. Arithmetic would be, you would say a sub 1 equals 2, and then you would say d equals 2, because then you're talking about a common difference, not common ratio. These are the patterns we're mostly going to talk about, but there are others. But in this case, going back to geometric, you're doubling it every time. My general rule isn't all that bad. It's a little bit simpler in this one. All you do for a, I'm just going to call it a general rule, is a sub n is going to be your first term multiplied by your common ratio n minus 1 times. So if you want to know the 15th term of this sequence, a sub 15 would be 2 times 2 to the 14th power.
Or can I raise a couple down to 14?
Or I'd ask you to leave it like that. Yeah, I would not have you multiply 2 by itself 14 times. That is just not the best use of your time in the 21st century.
Because I know like this is going to be a non-calculator test.
Parts of it will be. I do sometimes give a, in the past I've given a calculator part, where I ask you to actually do things with numbers that large, and a non-calculator part where I just like leave your answer as 2 to the 15th power or whatever. There's another example.
What is the general rule?
This is another example of a geometric sequence. Hold on a sec. What's a sub 1? Shell says 27. I hope everyone agrees with that one.
Mm-hmm.
What is my common ratio? I already told you it is a
Negative 1/3.
Negative 1/3. Excellent. If you see alternating signs, positive to negative, there is definitely a negative sign in your common ratio. Something is flipping back and forth repeatedly. What's the recursive rule? A sub n.
A sub n equals r times a sub n minus 1.
Yes. A sub n minus 1, yeah. What is my general rule?
A sub n
Equals a sub 1 times r to the exponent of
Give me the
n
actual
minus
a sub
1.
1 here.
on 27.
Uh-huh.
R to the n minus 1.
Yep. So you can find me the 50th term that way. It'd be annoying, and if I didn't give you a calculator, you might have something to the 50th power in it. But you could find me that. Tyler, I'm going to take you up on your guideline and ask you, without giving you any rule, you said it'd be fair to ask you for the sum of the first 4 terms without knowing a general rule for finding the sum.
For me, yeah.
Okay? Okay, so what's the sum of those first four terms?
Some of those first four terms, that will be, so, 27 minus 6, that would be 21. 20.
You guys agree?
Yeah.
You guys agree? That's what I got. So the sum of the first four terms is 20. Would it be fun for me to say what's the sum of the first 18 terms?
Then I'm using that formula.
Yeah, there's a formula coming up. So right now, that would again be tedious and complicated. Your sum formula for a geometric sequence is a really fun one that we'll refer back to semi-regularly. But the sum of the first n numbers for a geometric sequence, series they call it here now, is your first term minus your first, that's what I thought, your first term times r to the nth over 1 minus r. Your first term minus your first term times your common ratio raised to the number of the power of the number of terms you're talking about over 1 minus your common ratio.
Can you give an example?
Yeah, it's the sum of the first 18 terms of the sequence.
So
That'd be 27 minus 27 times 18th power over, yeah, 1 minus negative 1/3 or 1 plus 1/3. And because that's the 18th power in there, I don't think it's fair to ask you to continue with that one much further without a calculator. I'll quickly touch on one more example in the time I have, of an example of the geometric series.
R is 1/2.
R is 1/2. What's ace of 1?
That will be 1.
Does this look familiar?
it's his thing about how you're never going to get to it.
Zeno's paradox, also known as his thing about how you're never going to get to them. I like Michelle's description of that.
The Zeno part.
Yes, this is Zeno's paradox about how you can never get out of a room because you keep having to cover half the distance. And covering any finite distance, no matter how small, takes a finite amount of time, so how does this not add up to an infinite amount of time? Actually, Zeno's paradox...
There's an infinite amount of numbers in the sequence.
Yeah, well, infinity was an interesting concept when they were having this conversation in Greece many years ago. A lot of these times, starting at 1 makes it a little interesting as well. So, in order to try and leave the room, we must be interested in what's the sum of the first, I don't know, infinite number of terms.
2.
And
I
infinite
hope it's
equals infinite.
Hold that thought.
So
Well, if this adds up to an infinite number of
One
terms,
over
and Zeno's
infinity?
right,
One-
hold that thought.
1 minus 1 times 1/2 to the infinite.
Which we're not really supposed to write, but I'll put it there just for now.
Because technically.
1 minus 1/2.
Yep. Now, we're not really supposed to put infinite in the place of any number. What we're supposed to do, if this notation looks familiar from n behavior, is we're supposed to say, hey, what's happening which on this one, what's happening as n gets very close to infinity?
It's approaching 2.
Wait, see what
Is
you-
it? Or
Well, hang on a sec.
Isn't
Let me
it
break
1
this down a
minus
little bit
1
more.
half?
Pardon?
On the bottom, isn't it 1 minus
1 minus 1/2 is 1/2. 1 sec, give me one more second of your time here. 1 times anything doesn't change it, right? 1 raised to any power, however large, is still just 1. You can distribute an exponent to top and bottom of a fraction. Got my limit sign. So that becomes over 1/2, right? As n gets large, what happens to the whole fraction?
It's smaller.
Might as well be gone. What happens when you divide 1 by 1/2?
2.
So the limit, as we get close to infinity, of this sequence is 2. Homework tonight is not yet online, so I apologize, but make sure you write this down or talk to Michelle later because she'll definitely have it.